schedule. So for the next part, we will have our first guest lecture here, and we'll have Lu Ming from Pavilion, Shanghai, and who will give us a lecture on robotic simulation and programming, and also tutorials on the FU robot. Actually, is everybody back here? Good. And maybe before the lecture, Professor Yuan want to say hi to. Hi.
Hi. How are you?
Great.
Yes. So how about the students?
We just.
I'm coming here to visit the construction venue, and how about the plan to manufacture process? So when all the material coming, the day after tomorrow or tomorrow?
I think it's tomorrow. Tomorrow the steel plates. The panel will be tomorrow. Or yeah, maybe tomorrow. And the steel plates is gonna be here today. And it's ready.
So how about the design process right now? So actually, we want Yan Chao and Diana. They're planning to do an online exhibition on building C. So I'm actually talking to Yan Chao today. I want to you present the object, the whole process, not in this building, but present all the construction process to the online exhibition room. So I think tomorrow Yan Chao will give you a special model for building C, and you should address this pavilion into building C. Which part would you like to put this pavilion? That's first. Secondly, I think we need VR or AR technology, how to augmented use the technology to integrate the pavilion into the building C. So that's a challenge. I mean, Zhanqiang, they use 3D concrete to paint the bridge. I'm looking forward they can actually position the bridge into building C, but it's not a real bridge. It's actually it's kind of a visual realistic presentation. We have some real printing components, but it's not positioning on site. It's like VR, virtual reality presentation. So tomorrow I hope to make discussion with you, and if possible, I hope you can contact with Yan Chao to talk about how would you like to make the exhibition. So the next few days, I think at least one of you should focus on the exhibition, how to make the online exhibition work. Okay.
Okay.
Maybe you can subdivide the students into one group, maybe 2 or 3 who can especially focus on the online exhibition.
Yeah, we will discuss it.
Yeah, I think you should set up a meeting with Yan Chao. Yeah. And he actually have set up a team between Claudio and Diana. I think 2 of them outside China, and Yan Chao is in China. So it's like a 3 designers team already set up. So totally they will have like 6 days to do this exhibition. And Diana actually, his current workshop is the topic is online exhibition. So the challenge is how to because the past 9 years, everything is in building C. So I'm looking forward to still the scenario should be in building C as well. So that.
We lost your voice. Hello.
Yeah, I'm talking about the exhibition. Right now, they have a online exhibition team. 3 people, Yan Chao, Bianna, who is right now in Miami, and Claudia, who is right now in Romania. I think 3 of them right now working together, one in Europe, one in America, one in China. They are set up a team to organize to make the presentation online. So I'm looking forward that you should especially have an online meeting with them and then talk about how to address the process and the product, the final pavilion into that online scenario. So that's something you need to plan in the next 2 or 3 days, I think. And especially if we have enough students, if that's possible, we put 2 or 3 students or 3 or 4 students into the online exhibition part because we need some modeling and also how to present online about the process. And we can put all the student work, research process, and testing process, and the real construction process online. So that's probably could be interesting. And because there is not so many like physical construction work, so we are one of the team to implement robotics. So how to make scenarios, VR scenarios to present the process is a challenge actually. It's okay? Hans? Yeah. Mm-hmm. Yes. Mm-hmm. Yeah, I think Chaihua will help you to organize the online meeting with Chao and Vienna. Okay.
Yeah. And Professor Yan?
Yeah.
And Lu Ming is going to make a lecture on FU robots. Are you going?
Okay. Okay.
Do a small introduction of FU
I think
robots?
Lu Ming is a PhD, is a researcher in Fab Union past few years, and he will be a PhD candidate in Tongji very soon. And he is the chief researcher on FU robot. So today it's a great honor to invite Lu Ming to make the introduction of the FU robot. Actually, we only open part of the function of that because that's a platform we actually integrate not only KUKA but also ABB and UR. And in the future, more brands of the robotics is coming in. So that's just a part of the functions. It could be freely download online in footfall of Rhino. So I think that's something we want to set up to help the young generation. If you just buy a robot or set up a lab, so that could be very helpful to do some very easy work to play with robotics. So, Lu Ming, are you here? So welcome to make lecture.
Lu Ming, are you here? Okay. We can't hear you. Hello. I saw that my internet there may be not very well. Maybe you can re-enter the meeting room. Yeah, I think Professor Yuan just talk about the exhibition issues. Actually, every year there will be an exhibition of all the outcomes of digital future workshops. This year, the workshop is all move online, so they are now talking about new ways to exhibit all the outcomes.
Great. That sounds great.
We will talk about that later, maybe. We will wait for a while that Lu Ming will re-enter the meeting.
Mm. I'll put the stream on idle for
Yeah, now we give the time to moving.
Okay. Now can I begin?
Yes.
Okay. Now I give a quick lecture on robotic programming. Robotic, a quick introduce of robotic program. It's a it's a it's a little fundamental. It's for beginner. So I think it's all of you can will be helpful. And I will talk some basic usage of FU robots. Then I will talk something about the pose, to what is pose and what's the important in it. And next I will talk something of singularity. It's it's an important thing in robotic programming. Then I will tell something about transformation. Transformation is a little difficult maybe for us, but I think I will try to explain it. Then I will tell something about auto TCP. Auto TCP is I think it's easy way to use robotic program, but later I will discuss it. Final, I will talk something about real-time control. The real-time control, real-time communication is an important direction we can use. So let's begin. FU robots is a Grasshopper plugin. Is a Grasshopper plugin in for robots programming, offline programming or online programming. You can download in Food for Rhino. And you can see the tutorials in this place. This is the tutorial page. This is the website. You can this several tutorial is very basic for you, and you can learn it. I think you can learn it yourself. So today, I suppose you never use that. So I will take several minutes to show you how to use FU robots. So let's. Suppose I want the robots to draw a curve.
Sorry, may I? Yeah, before the tutorials, I want to add that I upload two files in the handouts Google Drive folder yesterday. You can find it in the day 2 folder, and it's the tutorials for today, and it is some basic script of FU robot.
Yeah, yeah. You can open the file and follow me. But if you don't download or never mind, you also can look just look at me. It's also okay. Uh, so let's begin. I draw a line, I draw a curve in the viewpoint, and put this thing and curve. Make a curve component and pick this curve, and we this divided the curve. So you can this curve has been divided equally, and now we can put the point into move component and connect the move component move command component to the robot core component and add a simulation bar to this core component and add robots. This robot is usually we use this robot for experiments because it's very small. So you cannot see
Hello.
any question.
We lost your connection. Lost. Hello. Blooming.
Hello.
Maybe you can restart your camera. Yeah, we can't hear you. And I think all of you can take this time to go to the Google Drive folder and find the files for today. Lu Ming, we can't hear you. Maybe you can try to open your camera again. Hello.
I can hear your chat bar.
Oh, I can hear you now.
Okay, so I can begin. I can begin.
But the connection sounds not good. We lost you again. Yeah, yeah.
Okay, okay. So now we can do this very simple program. Use a few robots. Can you see that this simulation? It's without thank you. It's without a tool. It's the simplest, the most simple simulation. But one thing I need to a little tips. It's better to turn off this button, because this button, when this is off, it's you change the input, it will not generate the component will not generate the offline file. If you open this keep on, you will if you change the input, the component will generate continuously generate the offline program. So it's better to turn off. So let's continue. Let's continue. So you can have this this part is SRC, the offline program. Offline program. You can see we generated this offline program. You can have a look. Then we put this program into a USB stick. Then we put a USB to the KUKA controller or ABB controller. Then the robots will move. So we can have a see. Can you see the video?
Yes.
It's very fast. Very fast to simulate, because we hasn't set up the velocity. Another thing need you to notice is this part. You can see A, B, C, this part. We didn't. This part is for rotation, but we haven't set up rotation. Why this part is 90 degrees? The unit is degrees. This is a little problem. So later I will explain. In robots program, there are two modes. One is line mode and another is a P2p mode. The line mode is robots move in straight line. And the P2p mode, the robots move from angle to angle. For example, if this is line mode. So if I change the divider, so there is only 2 points in the viewport. So if I simulate the robots you can see it's a straight line. The movement is a straight line. I can put it's a straight line. But if I change it into P2p mode, you can see it's not a straight line. This is a difference in difference usage because when you have when in 3D printing, when in 3D printing, we need to print the line is a very small segment. It should be a straight line, so it's used in 3D printing. But sometimes we use the pick and put the objects. It's not needed to move in a straight line. If we use the P2p mode, this mode is the fastest way, way to move. Because, for example, if as we all know, the robots have six axes. So we can, if I use one axis, if I use one angle, for example, the angle is 50 degrees, and the target angle is 60 degrees. So from 50 to 60, it should be a straight line. So it's a straight line from 50 to 60. Okay, so this is the fastest way for the robot to move. Next. Next, I will introduce the pose. The pose is the pose. We have the robot has 8 poses to achieve one point. In traditional robots, we have 8 poses to do the same thing. But maximum we have 16 poses to do the same thing. But it's this kind of robot we haven't seen because it's no use. It's not no use. It's just not usual. Usually we have the robots like KUKA, ABB, and UR have 8 poses. But it's a little thing is important. I have an example to show you. We must set up the start pose. Usually we have the robot. It's a good way to program. And as you see, this simplest example the start pose is traditionally this way, but I can change the start pose. I show you how to do that. This component is for pose. I use this component to set up the pose. I connect this to the angle component. So we connect them together. So you can, the start pose is this kind. It's very strange. I set up strange pose to begin. You can see, and this. You can see the robots move a little. You can see the robots move in this pose. It's a little strange. It's very strange, but it's controlled by the starter pose. I just use a strange pose, so the whole simulation is all strange. If I disconnect them, so this is traditional, is usually pose. So the start pose is important to programming. And another tips is if you also can change the pose, even the start pose is strange. You can do this. Right click the component move. Select the 110. So this way you can see the simulation is also okay. So you can feel this. The pose is you can change the pose by start pose and or in component movement command component. It's up to you. Another thing is this is KUKA, and also ABB is also the same things. ABB is same thing, but the UR is not the same. UR is a little complex. It's not controlled by this component. You cannot component to select the pose in component. You are just calculate the pose from the previously pose. It's a little complex. So later maybe I will tell these things. So to the next. So it's better to set a pose at first. It's a greater in good manner. Now another topic is the singularity. Singularity is so important, so you cannot ignore, neglect. You cannot. You should take care of these things. There are three kinds of singularity. The first one, I should use pen. The first one, this is the first one, is with on the root. This point is waist, like a human hand. This is the waist. This second is waist, elbow, and the shoulder axis in one line. If you see this is the robot. So you can see this is an offset, a little offset in this place. So in fact, this line is so this line and this line is not a parallel. Just notice that is okay. The third one is the most important one. It's called A5 singularity. It means when the robot's A5 axis is near or at zero angles, the robot will stop and give you an error. I will show you. I show you now. Let's recover the traditional pose. So you can see this pose is okay, it's very okay. But if I move a little up, you will see it's also okay. I will need to a little. So this time you can see not very obvious. So this is you can see when the robots move in this place, it rotates very fast. I show you the graph. The graph will tell you everything. The graph, you can see the A4 and the A6 is this blue and the yellow line. When this A5, this dark red line is near the zero, so this A4 and the A6, the rotation is very fast. The more steeper the curve, more faster the angle velocity. This is not a good thing because when every robot has this angle limit, if you too fast the angle velocity, the robot will stop and give you an error. So we should not let the A5 to near the zero. So we need to put the objects a little down in this example. So you can see this is so nice. So you can see the curve is not steeper as previously. It's good. let's go to a next. So let's talk about another topic. It's transformation. This is the most important concept in robotics. I'm sure this is the most important things. So how to move an object in computer, and how to describe the rotation and the movement in 3D space. These two questions has the same answer. The answer is transformations. We should use transformation to do these things. I will show you a very simple example. Suppose there is a rabbit located in 1,0 position. And this is X, this is Y, and this is C direction. But in this example, we don't use C direction because it's a 2D example. So forget C direction. We just use X and Y. So my question is, if I rotate 30 degrees, where this rabbit located? It's easy to answer because if I do this, you can see this is cosine 30 degrees, and this is sine 30 degrees. So this is X is cosine 30 degrees, and Y is sine 30 degrees. This is the location of this rabbit. It's so easy. But another question is if I erase them. Another question is if I put a pointer here, this pointer, its coordinate is 0.5, 0.3, this kind. And how about when this pointer rotates 30 degrees around the original, where is the final location? It's a little more complex than the previous questions, and you also can do that. You without transformation, without a matrix, but if you use matrix and the transformation matrix, it will become more easily to do this question. I will show you. I construct a matrix, transformation matrix in this way. This is this. This is this. This is this. This is this. So I construct. You can see this. This is the coordinates of A prime. A prime is this. This one, this two is B prime coordinates. So it's easy to remember. We call this rotation transformation. So another thing I must to introduce. Suppose this is a matrix. This is a multiply. This is a vector. So a vector is a coordinate of one point in this example. For example, we have a point in 0.5 and 0.3. So the vector we can write 0.5 and 0.3. This is the vector like this. So we multiply the matrix and the vector. Use this way to multiply them. A plus E plus A and E plus B and F plus C and F plus F multiple D. It's easy to remember. You can do too many. I erased them. And you can do this E to write down here and F to write down here. So you can multiple. So it's this one. You can have calculator by hand or by another MATLAB or even in Grasshopper. You can do this. So in our example, we construct the rotation. This is a rotation matrix. This is the vector 1, 0, because this point we have 1, 0. So the final answer is this one. It's obviously it's right because so we can do this also in Grasshopper. Let's have I will do another example. I will multiple cause this rotation matrix to (1.5) and 1.3, and let's see the answer. Use Grasshopper. I take a new document and I create a new point. Its location 1.5 and 1.3 and 0. So this position is I should delete this one. So you can see this little point. This little point we create. So the next thing I will construct a matrix. In Grasshopper, there is a component for constructor matrix. this is for rows, this is for columns. We can see this rotation matrix. We have two columns, one, 2, and two row 1, 2. So we input these two to them, and in this position, in this rotation matrix, this is you can do this by calculator if you're interested. This minus this is so I move a little wider. So I can input this number in the Grasshopper to construct the matrix, rotation matrix. So we can display the matrix. You can see this is exactly the same with this one. So this is the rotation matrix. This one is rotation matrix. And next, I will do this, create this vector. I use the same way, but the vector is 2 rows and 1 column. Next, you can see there are 2 rows. There are 2 rows and 1 column. So, and then the number we will also change. This time is 1.5 and 1.3. It's okay. So this is the vector. This vector. So I need to multiply these two matrix, but it's strictly speaking, there is no good multiplier component for matrix. So I can create one. It's very simple to create one in C#. I put a matrix A equals to X as matrix and matrix. So A is equal to A E. So you can see the answer. This is the answer. 1.283. The X coordinate is this. The Y coordinate is this. I can choose a little bigger, longer the digital. So I can try to verify this. I rotate. I'm sorry. Rotate the center of rotation is the original point, and the first this is, I should take this, and this angle I should take 30 degree. So this is the new point. We look at the coordinates as this one, as the same with the matrix, rotation matrix multiply. So this simple example tell us we can do the transform, rotation, and move and any other transform use the matrix. In fact, in computer graphics, all the operation is in matrix. Also in robots programming. Also in robotics and internal is the matrix. So I have already introduced rotation matrix, but in fact, we also can meet the move. The move is also can be represented by a move matrix. In this example, the rabbit, when after rotate 30 degrees, we move the rabbit in its x direction forward 1.3 meters. And how to do this, how to calculate the new location? It also can be calculated in transformation matrix. The rotation of the move transformation is construction like this. You put the x in this and put the y in this. Because y is 0, we didn't move y any, and so we move the x in 1.3. So this is move transformation. It's a little difficult to take time to explain why construct like this. But if you're interested, you can refer to any computer graphics book or linear algebra books, textbook. And this is for matrix multiply. Previously, I introduced the matrix multiply vector, but this is for matrix multiply matrix. A little complex than previous. And the reason why I needed two matrix multiply together is I really want to combine the rotation and the move, these two kind of things together into one transform. So if I finish these things, I get a combined matrix. It has rotation and movement. So if I multiply, if I multiply a vector here, for example, I can get the final result of the new location. It's include rotation and movement. Yes, you can. This is an example. In the example, you can see this is the vector. 1 is 0 is. This is 1 0. Why this is 1? Because we use a why this is 0, 0, 1? Because we use a treaty. Its name is homogeneous coordinate. It's a little complex. You just have a feeling, just okay. If you need to, you can refer some books. But this works. You can get the final results. This is X, this is Y, at this location. This we have already talked about all as 2D so, but in 3Ds we just add this column and this row. So this will become a 4 by 4 matrix. It can rotate an object in 3D space, not only in 2D space, and move in 3D space. You can see this is X, this is Y, this is C, because this is the 3D coordinates of one point. So how this transform matrix related to robots? It's a question. I can explain this to you. You can see, for example, this is an angle. It's rotate. It's like this. Yes, it's rotated. It's also rotates, and without rotate, this position or this frame also move in y direction. This green means y. Maybe this is 1 millimeter long. So this is the rotation matrix and the multiply move matrix. So we can combine them together to a matrix, to a transformation matrix. We call this T2, 3, because this is 2, we move to 3. We call it T2, 3. If T has an if T this this is A2 angle. This A2 angle now is 0. So if we a little move rotate this part, for example, we rotate the a little, maybe this is also 30 degrees. So this robot is in this place. So we can construct a sine this is cosine. This is cosine. This is sine. Oh, I'm sorry. This cosine, 30 degrees. This sine, 30 degrees. Minus sine. This sine. This cosine 30 degrees, and this 0, 0, 1. This is 0, 0. This is 0. This is 1000 because this in y direction. is 1000. This is 0. In C direction is no. In X direction is no. This is 1, 0, 0, 0. This is the homogeneous coordinates. So this matrix is the whole matrix for F2. We call T2, 3. So in robots, we have a lot of axes. T1, 2. This is T2, 3. This is T3, 4. This is T4, 5. This is T5, 6, and T6 to flange. Flange is these things, and T flange to TCP tool. So we can multiply them together. T1, 2 multiply T2, 3 multiply T3, 4 multiply T flange to tool. So we can multiply them together. We can get a final T1, 2 transformation. So if we get to this transformation, we can know the TCP, this 2 position, just to multiply them together and plus and together, yes. So yes, this is the same thing I have already said. Another thing is in there's three kind of 4 kind of rotation representation in robotics. And the KUKA use Euler angle. Euler angle is the most easy to feel, and universal robots is rotation vector. Also, it can be called Lie algebra. Lie algebra is Lie group. It's related to Lie group. And the quaternion is these two kind of quaternion and the rotation vector are not so easy to comprehensive, and this Euler angle is easy to. You can see this rotation path. This is the transformation. This part is for rotation. This part is for movement. And in FU robots, there are a lot of components to do this transformation. You can convert the Euler angle to rotation vector, and vice and inverse, and do the same to you can do this by this component. This is Euler angle. Euler angle is rho pitch yaw is very famous in a lot of places. This pitch is around this rho is this yaw is it's in KUKA, it's the same. This is the normal vector of flange is the C direction. This is X is down. This is why. Also in the root is this. So if we want robots to move, we should to change the root transformation, and the worker base is not so usually used. So I didn't say. And I now tell something, show you an example on roots. I go to I delete this and do a new curve. I
Lumi. Hello. Hello, Lumi. Are you still there?
Can you hear me? Hello?
Yes. Hello.
哇，这电视好大，
对啊，真的
跟
好大。
我们家差不多。
Okay. Hello.
Hello.
Hello. I opened the video and open the video.
You know the connection is not good. Hello.
Can you hear? Hello.
Yeah.
How? Okay. I continue.
Yes.
I continue to this example. So I can move the pointer to anywhere the robots will move. And also I can make a box to simulate this move, move car. Can pick this mesh, use the mesh components, and you can see. So I had this okay. Hello.
Yeah, we can hear you.
Okay.
Yes.
Okay. So I continue. You can see when I move the point, the robots will continue to move. Okay. Another topic is about auto TCP. What is the TCP? TCP is a tool center point. For example, what is a tool center point? This is defined by yourself. You can define this as a tool center point or do this or this. But the TCP is defined as a transformation from the robot's flange. It means the TCP is a transformation, and the transformation is from the flange. The flange is this one. It means we start from this one to this one. We start from flange to TCP. This movement or this rotation we call transformation. This is ABB transformation. This is a flange of ABB. This is the same with KUKA because the normal vector is C, this down is X, this is Y. It's the same with KUKA. The flange coordinates framework is same. So you can the transformation is begin from flange then to the TCP. You can see the whole process is contain the rotation and the movement. So this is three kind of robots, flange coordinates and TCP coordinates, the default setting. You can see the most important thing you can find that they are so different. This is not different with this. This is not different with this. But KUKA flange and ABB flange is the same. But except this, it's not others is not so is so different. So it's harder to remember. You can check this image if you want. And the problem is you should you should notice one thing. If I divide a curve with a lot of points, the default frame is for one point is world coordinates. is like this. But this is default coordinate. We in AVB the default TCP is C direction is downward. So we should if we want to like this to move, we should move this target framework around the y axis 180 degrees to rotate. So after rotate, this become the same. Because this go to the down, go down. This is the what the auto TCP mean? Auto TCP mean is we in every robot this rotation rotates 180 degrees is automatically for you. In KUKA, we should the auto TCP rotates 90 degrees around the y direction. In ABB is 180 degrees. So we can remember the first slide. You can see this y. This is 90 degrees because you use auto TCP. Every robot rotates for you for easy use. But this is not a good thing always like this. You should use it's better to use manual TCP because in manual TCP you can exactly to see what kind of TCP you really use. It's just rotated the TCP by yourself in a Grasshopper. For example, in KUKA, 90 degrees around the y direction in ABB. Yes, you do this itself. So it's good to, it's better to use manual TCP. Another topic, the last topic is about relative control, real-time control. Real-time control, you can see. The robots follow this wood brick and move smoothly. This is the whole work is first the Grasshopper. In the Grasshopper, we read the sensor. The sensor in this example is the camera. So we in Grasshopper, in every robot, we read the image from the camera and analyze this image, and we get the position of the wood brick, and later we in every robot we send the command to robot. In this kind, we use RSI to do this work. Then robots receive the command. He will act immediately because the ISI is a real time. It will act immediately. And when finish act, the robot KUKA will send back some message, some information to Grasshopper and tell Grasshopper I have finished and the position of now is where I am in which position. And the sensor, we can, in this example, the sensor is connected to Grasshopper. But if we have a lot of sensor, we can put the sensor into rows and use rows bridge to communication with Grasshopper. This component is for communication and real-time control with robots. And this component is for camera, for some image recognize and image process. You can see the image how to follow this wood brick. So thank you. And I think it's enough for you to in 1 hour. It's too much things maybe. Thank you for listening.
And thank you for the lecture. I think there are several questions in the chat window.
There are several questions.
And Jakob have already answered one, I think. There's one says that don't understand the script of in your slide, which says that all transformation should be around the AX.
Can you say again, Chaihua?
You can see that in the chat window.
In the chat, I'm sorry, I don't understand the script of mean.
Yeah.
Says all transformation should around the C. It means that we defined the truth or transformation. Define this.
Maybe you can share your slide again. And
yes. Wait. The slide. I should.
And when you're talking about the transformation.
Okay. And is this question? This.
No, it's before that, I think.
This.
No, far up. Up. Which is that? Still up.
Still up. Okay.
Yes, the 22nd slide.
22nd.
Yes.
This. Yes, I understand you. Yes, all the rotations should around the c-axis. This is this is a you should you should feel this as a law. All the in robotics, all the rotation happens on c-axis. This is a law.
It's defined by the robots. When they make a rotation at each x, the coordinate at that x is it is defined to be rotate around the x. I think. So it's defined by
Yeah.
by
If you want to look some to deeper to learn, you can to see some books on robotics, and it's very detailed to explain these things.
And further question is that is all the rotation around the x is for avoiding singularity?
You say all the rotation around the c-axis is to avoid singularity?
It's a question for you.
No. It's not these two things not relative. No connector.
Okay. So there are no connection between this principle and the singularity. And I think there's a
Okay, I can see the chat.
Oh, that's great.
Any question?
Oh, I think we have a question before this. Is that does FU robots work with Mac OS X system?
No Mac, just Windows 10.
Just Windows 10?
And the source of image process encoding is now work in progress. You can see some of them is also transparent. You can see it's not finished. When they finish, I feel Fab Union will release, I think, after finish.
Now we can continue with previous ones. Do you offer any source for image process coding?
Oh, I use A4 library, computer vision library, A4.
Maybe you can test that in the chat window.
What's your image process sequence for object detection? This is yes, it's up to you. It's first binary or then the filter color, and this is not a lot of things you can choose. It's not strictly must no, this it's up to you. Or the effect grid is good. Any specific lighting condition or surface? Yes, because the image, if you have some highlights, it will reflect or reflect very much, it will can't recognize, it will fail in image processing. Any question?
Oh. I will read that, and I also paste that in the chat window. First, can you explain how we sync the G code while working with two robots?
I understand you. In KUKA, we use sometimes we use Roboteam, but it's I'm sorry. We sync the G code, and I know. You can use the communication to robots. For example, if you have two robots, you can prepare two computer with the FU robot, and these two computers can communicate by UDP, and the FU robot has UDP components to communicate. And in this way, you can, without robot teams, because all the sync is decided by FU robots by yourself. Okay, that's my answer.
And one more question. I will also paste in the chat window. Could you explain? Oh no. Does this plugin only work with its predefined robot?
This question, I show you do the customized robots. We have already the customized robots. You can see this, and but just for KUKA and the ABB, because UR is we have 3 kind. I think now is okay, but KUKA and ABB is not so much. So I have designed customized robots. You can see the tutorial on the website how to use this customized robot, but just for 6 degree of freedom robots. You can search the tutorial on my FU robot document websites. Okay.
The last question.
Oh, okay. I can't find the building. Yes, because this image tool is we haven't released because it's only still in work in progress.
Okay.
Some other logo, that's the table. Yes, I some table as rotation is for external, but now we in a few robots haven't do this rotation external table. And in the future, we will do these things.
Yeah, great.
Okay.
But we have external x as a linear axis, right?
Yes.
Okay. Okay, great. So if you don't have any questions, one more question come from the online auditing student. Is asking what does a robot track component do, and maybe
the robo check component is it's important. This is important to check. It's important to check the robots. You can see the here. You can see my screen. Connect them to the robot checker. If everything is okay, it will show okay. But if you not far away from, it will tell you out of range. 10 means at 10% in whole procedure. In whole simulation, 10%, the position is in 10%. So as in a long, if your simulation is very long, the check may take a lot of time, may make your computer down. So you need you better to set this to a number. This it means in whole simulation you just take a sample 64 samples to check, not a lot of. Usually we use 1,000. It's okay to take 1,000 samples to check, because if we take a lot of samples, too much, the computer will take a long time to calculation. So in this we can save the time. Okay.
Okay. Thank you.
Thank you.
And thank you again for the lecture. And I think the tutorial today is gonna be like this, and we still have some time to do our skill up, interactive skill up. So I think Lu Ming have already introduced some basic some knowledge about how the robot works, and it's trying to help you to understand the way the robot works and how the FU robot is developed. And but what he doesn't introduce is how to actually use FU robots to simulate your own robot. And I mean, some of you have the experience working with robots, but I think most of you don't work with robots before. So maybe Lu Ming, would you like to do a very little tutorials on how to use this plugin. Or maybe I can also do that. What do you think?
I have already introduced how to use the FU robots, but a very simple example.
Yes, yeah, and yeah, maybe the student can work try to use the program we provide in the Google folder, and if you have any question according to that files, you can post forward now. Yeah. Yes. Okay, maybe we can just open the files and show you how it works, right?
To do some web and place simulation, right? I will use the introduce FU robots do a little example how to use this. First, we do the components to generate the points, and use the pointer to generate the move command. And use the move command, we can directly link connect to the command, and you can see this is file off. Now we want to generate a file. We click this on, but where is the file? Where is the file? You can check the file in your desktop, because if you this Grasshopper file is not hasn't been saved, so the default location of offline program is on desktop, so we can check. Yes, this is the offline program. You can see we use auto TCP. This is 90 degrees in B. It means a Y direction rotates 90 degrees. So if we save this file in this place, maybe df so we can get the offline program. I need to do it again. You can see this is the offline program we have already generated. Then we save this file into a USB. Then we put this USB disk to the controller, and loaded this program into controller. We can let the robots to move. Chaihua, I think it's a simple example. Yes, okay.
Yeah, good. Maybe as you know, some of the students have never worked with robots.
Yeah. It's harder to listen this lecture because if you don't never use robotic before, it's hard to understand, and maybe it's harder to maybe.
Yeah, but I think it's okay, and the lecture is great to help us to understand how the robot works and how the program works, and also the students will have the tutorials in files, and they can simulate themselves, and we will also have one more robotic programming tutorials on the 5th day, I think, and that's where we try to teach you how to simulate your own project, and that's very specific to our design project. So maybe if you have any question, you can leave a message to us and send an email to us, or you can also leave to the 5th day, and we will talk about the programming again. Is that okay?
I see a question. Do the curves we draw need to be a single connected curve for robot to generate the code, or they can be separated? This it's better not to separate the curves. If you separate the curves, independent curve, it's not so good in 3D printing, because 3D printing every point should be equally divided.
Yeah, we are not working on 3D printing.
Okay.
Great. Any more questions? Yes, for George, are there more resources, tutorials online? I think so. At the first of the lecture of Looming.
So we will be mainly simulating the assembling process. Oh, this is for you, Chad.
Yes. Yeah. So we will be mainly simulating the assembly process of the pavilion. Then, yes. I think for our workshop, that's our one of our tasks to try to simulate the design that you developed, right? It's today we are just trying to get you to know how to use few robots and maybe how robots works, and the final destination is trying to use this robots to fabricate the building system we are developed, and get you to know how to integrate the robotic fabrication process in your design process, and let you get better understand how the integrated process works. Yeah. Where are we?
Can we?
Are there more resources, tutorials online? And I think Vicky have already pasted the tutorials website in the chat window. It's fabionian.github.io. You can get started with the tutorial there. I think the question from Alireza is also for me, right? Can we predict the time of assembling in the plugin or in the controller? Actually, when we predicting the time needed for the assemblies, we need to do some experiment to see how many times we need for maybe one element or one group of elements, and then we try to yes, the experimental says much more than the simulation. But in the simulation we can see whether the fabrication process is all right, and is there any collisions, and is there any element that is out of the reach of the robot. And I think that's what we want to do in the simulation process. And for the predicting of the time, we need to first calculate how many elements we have and how many times we need to fabricate one element or a group of elements, and then predict the total time for the whole structure. And from Chris, should we compose all full movement paths, or can we, for example, just specify more high-level pick up point and the drop point of our timber piece, and can it generate paths on itself? Yes. For this question, I think I will show you in the 5th day of the robotic simulation of our developed project, and you will see how we define the points. How we define the points that we pick up the element, went through the element. Went the element through the glue station, and then put the elements on at where we designed, and then nail it. And after that, we move we lose the timber there, and then nail the timber at another end. And I will show you how the whole process and how to define the whole process in the plugin. And I think that you have already seen a video that simulated in the introduction of this workshop in Jakob's introduction yesterday, and you will also manage to make that yourself in the final simulation. One question from Ben. Is there a glue tool component? You mean a component in FU robot, or a tool component on our platform? Actually, I'm not very sure about what you want to ask. FU robot? No, it doesn't have a glue tool component, and it doesn't have to have one. And we have the glue station on our platform, and what we want to do is just to define where the robots should go, and then we give signal to the glue station. It will just put the glue on the component, and then we move the component away. So we don't, in the whole process, we just need to know where is the glue station on the platform, just the location. But we don't need tools defined in FU robots. You will get to know that yeah, in the next robotic simulation tutorials. And the next, do you have a judge robot setup file reflecting current situation? Yes, we have that, and we actually we are preparing that for the 5th day, I think. And today we just what we want for today is just want you to understand how robot works, and you can simulate. You can learn how to simulate a very simple robot with FU robots here. Yes, you, and the answer is yes, you will have the robot set up. And the new question from Alireza, for our work, the TCP would change location by location because our robot moves with wheels. Actually, it will move, but you know the TCP is it's it's a no it's how to say that it's a 3D coordinates that 3D frame that is relative to our robot base, or relative to the robot flange. So as our robot move, the relative relationship between the tool and the robot doesn't change it. So it won't influence the code of the robot. So what we need to do is just move the base of the robot, so the robot will change the change will move from the world coordinate to another to where we define to a new location. A question from Mohammed. Yesterday, it was shown that the mobile platform was controlled from Python directly. Is there any specific library for that? I'm not sure what's the Python script. Yag, do you know what's Yag? Do you know what's that would be great. Oh, we have more. Further question from Alireza. So we should define the TCP after moving the robot, right? I think yeah, as the TCP is relative to the robot itself, so we don't have to really define the TCP. And I think that's all. And we still have some time. Maybe we can go through the individual project from yesterday. Jakob? I think Lumi is still sharing. Yep. Very impressive project.
Yeah, I can give a short introduction now. as in what you often see that in terms of facades, there is a certain distance between columns, like for example 5 meters for as well the inside as the outside. But when you have a circular building like this with an inside facade and an outside facade, you have a different number of columns on the inside ring and outside ring, which means that traditionally you would solve it like this with straight beams and multiple, putting in more structure in it, while the floor itself will not need that that span. So I was really wondering if we, with these kinds of combinations of beams, could reduce the amount of beam length and somehow combine it. And as a first exploration, what you see in the next images is that simply assign a bigger dimension towards where things collide.
Cool.
That's it in short.
Yeah, I think that's super interesting. Then Abel is also quite cool. Pretty impressive cantilever here, I guess.
Yeah, this is what I was trying to do actually, to increase the span of the cantilever somehow, but I ended up introducing some some column inside.
Okay.
I mean, here at the arrow tip. At the beginning, I was just imagining like multi-story building with 2 apartments. I'm not sure how it's gonna go farther down the road, but I'll try to keep as cantilever span as possible. I'm not sure how much it can get with structural optimization.
Yeah.
Later on.
Sounds interesting. We'll look at. We can actually look here. Great. Forgive me if I misspell your name. Xuexin Duan, is that correct?
Xuexin Duan, yeah.
Okay. You want to say something? Looks pretty extensive study of, I guess, magnetic field networks.
Just a quick studies for the magnetic field, just thinking about besides the structure optimization, like minimize the material and what else we can bring inside the space. Is a kind of the magnetic field kind of have the maybe is a kind of semantic layers to the space, because I think that the structure for any reasons can be like optimized. And so this kind of pattern, for example, start with very simple grid, and this to put the charge, and also can be considered as where the location for the column, and also can be considered as very abstract, the attraction point for like each event or the social interactions in the space, and kind of give a meaning to this space and the articulations for the ceilings. And also can be easier to integrate with the lightings and the thing like create a second layer for this structure patterns.
Okay.
Just a quick different updates, but the real the beam, the layout of the beam, I didn't go further, so it's still like a kind of mess. You can just quickly flip through all of them. So basically, it's like a same grade, like a same column, but you can generate a different meaning over the different spatial phenomenological organizations, or you can call it a semiological articulation.
All right. So to guide the inhabitant of the structure through the different spatial articulations.
Yeah, I think it's just very abstract.
Okay. Okay, and this is the beams. It's like one.
Just a quick test to run through the scripts, but
okay.
I didn't like go details to adjust the layout of all the beam.
Yeah.
So still like.
Yeah, that's okay. It's still pretty impressive study. I would actually be interested in seeing in a bit more detail how the logic of these lines actually differs between between the different versions, right? I guess it would be quite amazing if there is also a certain connectivity constraint within those fields, right? Or I guess maybe a couple of those settings of different charges already showcase somehow a very very structurally also valid solution, right? So I guess it's not only like a visual study, right? It could be also interesting in terms of
fields, because I think this have a kind of same solutions from the structure point of view. They can have some like similarities.
Yeah.
So maybe can use the structural optimization softwares. If like doing another layer of this structure optimizations could be get like similar results.
Yeah. Yeah, I mean, I guess per se the logic of magnetic fields is very different from like a structural topology optimization or even stress lines, right? But there might be certain sets of charge combinations that actually produce networks that are somehow performative, right? So I think that would be super interesting to get a bit more insight in how they are developing.
Yes, I think. And I think tomorrow we are going to talk about the networks, and I think we are also one network we are going to talk about. It's also a similar network that will resemble a stress line network, but we did it in a different way. And actually, I'm also quite interesting when to see in the chart of magnetic lines, and actually when you are trying to change the different charge at a different point, you may actually get the pattern very similar to the stress pattern, but obviously without any structure principle inside. But I think it's a good direction to develop on to maybe as one of the patterns that could be one possibility for the final structure exploration. Yeah.
Okay, thanks.
Okay. George also has a very dynamic exploration. You want to say something about it?
I think it's self-explanatory. It's a much simpler solution. The idea of this was to have this as a single component you could you could array in a circular arrangement.
Okay. So the triangular slab or this triangular component would be kind of prefabricated and then brought to set or kind of arranged sequentially.
Yeah.
Cool. Okay, Jennifer made also some very interesting study. I guess that deviates very far from the topic of a slab, right? But,
yes, I considered it to be like a more conceptual experiment. So I didn't have much of a slab in my mind. I just wanted to try something that is three-dimensional because we will mostly be working in 2D.
Yeah.
So I wanted to try something that was a little more complex.
Mm-hmm.
So I just took a Fibonacci spiral, created a 3D curve of it, and tried to do the same logic that we did yesterday in class.
Cool. Liu and Yun, barreling beam arrangements. Yeah, we hear you.
Okay, I just find the helix curve really special, like the galaxy spiral and the star expands outward. Your spiral shape with the center of the circle, and also I find this structure maybe kind of like a decoration, and the structure is continuous like a whole. So, and also the columns may be placed on special points on the curve. So, just try this. Yeah, thank you.
Cool.
Yes, so my concept here is quite simple, just a leaf branch pattern here that is mimicking a Amazon water lily, which is known of having a high efficiency of load bearing, and the maximum radius in the pipe is affected by the length of the trail curve, and the gradient is controlled by a graph mapper. So I think that for the development, these patterns should be somehow situated according to some certain environmental constraint, like some load things. Yeah.
Mm-hmm.
So in this one, I wanted to derive a shape from a triangle and create a density difference in the packing of the wooden members. Like it's not as effective over here. And after my question today, the tutor told me that it'd be better to just have a single curve for the robot to place the wooden members. So that's something I'm going to explore in the next iteration. And probably I'm also thinking of just having a central column as a support instead of having three on the edges, and see how the cantilever would work.
Mohammed, you want to say something about your exercise?
Hello to all my friends.
Hello.
Can you hear me? Do you have my sound?
Yeah.
Yes.
I just had a concept about the infinity forces that going throughout two columns between the beam between them, and I just wanted to control the density of the timber woods between the columns, that where the pressure is more powerful in the beam, the forces that appear like pressure on the upper part of the beam that connect to the column, and between them, when the tension forces are more powerful on the on below the beam, I wanted to just have more timber woods for just conveying the force of the between two columns. Just this.
Okay.
Thank you.
My computer is freezing for a second. Okay.
I think my approach is more of like a decorative, like symmetrical approach of it. I think initially I was wanted to create a Voronoi pattern, like to manipulate a radiate grid of it from the center of the column. But I find it is kind of tricky to figure out the direction of the H lines of the Voronoi pattern, so that I try a arrays and kind of operation to create these sort of patterns that expand to multi directions, and just did a few experiments on it.
Cool.
Yes, sorry, can you hear me?
Yep.
Yep.
Cool. So I was thinking this could be in the idea that like maybe being able to change the density of the members is probably most efficient when you have like some really indeterminate structure like a lattice roof or something like that. And so this was just looking at a way of making like a short cantilever roof that provides like in-plane diaphragm stiffness and like bending rigidity through adding these additional beams. But actually, since then, I also have another idea from a different project that I previously worked on that I might pursue instead.
Okay.
So that one. Okay.
Cool.
I used the friction of a kangaroo plugin and form the baseline formation, and the curve attract and squeeze each other, but not overlaps. So I used the Grasshopper source file yesterday and trained its build patterns through some simple rotation, scaling, and random selection, and forms the I think it's like the mitochondria pattern with the comparison of the line and the plane. Thank you.
Great.
Hi, can you hear me?
Yeah.
I was trying to build a 3D structure with the method I learned yesterday. I'm doing so to practice about the data structure of the Grasshopper I'm right now learning. I built this since the I want to build this with the structure, like the power and I don't know how to say that. As I haven't learned the topology analysis, and so I used the distance between the center of this cube and also the every point of this of each line to define the structure.
Okay. I guess for now it's totally okay to experiment in more three-dimensional things. I guess that applies to Jennifer, you, and John. But just be aware that this is a structural system that I think definitely would be possible to do, right? But with the
yeah, it's a random generated.
Yeah, no, but with the current fabricator, we're mostly interested in this kind of system where you have like a flat surface
Yes.
that is then reinforced. But for today, this is a great study. Just for the next days, then I guess focus towards the slab topology. Okay.
Got it.
Zhang?
Got it.
Are you here?
Zhang Yicheng. Not here?
I'm here.
Oh, yeah.
Hey, sorry. Hey. Because we all like to enjoy the cool under the tree. So I want to imitate the intention of a growing tree, but my ability has not yet realized it. Just imitating your case. Thank you.
All right.
Well, can you hear me?
Yes.
Well, let me give a short introduction about my work. Yesterday, the lecturer said that this research is basically for the 2D print, so I want to have a try whether it's more difficult for 3D. So I use some algorithm to generate some curves and project in the 3D surface and 3D surface. And although I make some small mistakes in the Grasshopper files, and I use some complicated way to solve it, and I even don't know whether it's more difficult to write a Python file or the Grasshopper file in the last few days to help the robot to build it up. It's just a try. Thank you.
Great. This is, I guess, the bar for the virtual drinks on Friday, right?
Hi, can you hear me?
Yes.
Yeah, so my idea is basically, after all, it's a structure. So instead of explore some certain pattern in 2-dimensional, I want to explore its potential in 3-dimensional space. And so I made some adjustment to the script because all these timbers should be placed in the flat plane. So as you can see, it's just very basic try, and looking forward to explore more. Thanks.
Yeah, it's a cool exercise. As for the others, I guess here applies that towards the next days we would want to move this in a more, let's say, slab topology system. I think it's a super nice study.
Yeah.
I guess very elegant. Okay, did we miss the someone who still wants to show their work? I'm not sure when I downloaded the picture, so if you upload it very recently, then maybe I didn't have it yet. Also, I guess some of you didn't upload the JPEG files, so I'm not sure if I converted all of them. If someone wants to show their explorations that we might have missed.
No.
Okay. That's good.
Yeah, although this is just a very basic study and a very basic scale up of Grasshopper, but I think we have already seen some potential in your design, and and also some of them may also have the structural meaning in your predefined network, I think. And I think some of you may go further in the next few days, either based on this very basic exploration, or start from the very beginning. And I think in my mind, most of you are ready to design the structure we're proposing, and I really looking forward to the result. Great.
Yeah, I agree. So I guess tomorrow we're gonna give also a bit more intro to what we are hoping to guide you guys through until Friday in terms of your individual project. We'll have a bit of a briefing in the morning, and then also tomorrow we would ask you guys to form groups of like 2 or 3 people in each group, and for that maybe you can just go through the list of the participants with the respective time zones, and maybe by looking at the work you also might already understand with whom you want to work with. Maybe you have like similar ideas, or you feel you would complement each other very much, right? I guess for the structural engineers amongst us, I would say it would be great for you guys to work with someone who is not a structural engineer, and for the architects, obviously is the opposite. So I highly recommend, or I guess we highly recommend interdisciplinary groups, just because the quality and the depth of the work is gonna for sure benefit from that. But yeah, in the end, I think we are gonna leave you to form groups by yourselves. I guess we can just use the Google Drive sheet for you guys to self-organize into groups. I guess we're just gonna make a column where you can just write your group name as soon as you found some members.
So limit the group number so we don't have too many groups.
Yeah. I guess in the end we are looking for like 10 groups, right?
Yeah, 9 to 10, it's okay.
Yeah.
So maybe we only have 10 rows in the Google folder, Google form.
Yep.
And you can fill your name in that.
And then I guess there was a question from Sanas Tagami on the live stream, which I get. And we have more questions.
Yeah.
Okay, but let's do hers first, because I think that's also relevant for the design, right? So it's writing, I'm wondering to know about the overlapping elements and what we have to do for not having the overlaps, right? And I guess that's exactly what we're gonna discuss tomorrow. Jai-Hua is gonna give you
tomorrow, maybe the day after tomorrow.
Or the day after tomorrow, sorry. So this is obviously the challenge, right? So in all of the examples that we made yesterday and that you guys explored until today, we have a certain agency over the beams, right? So we kind of control them in a computational manner, but really there is one big problem that would keep us from building such structures as they're proposed now, which is that some of the beams are flying in the air, right, and some of the beams are overlapping, and this obviously is not super trivial to solve. But I guess there's a couple of strategies that we can employ. And along those lines, I think this might also be maybe one of the things where for us it's really open in terms of how serious you want to take this and how far you maybe have already experience in coding and scripting, right? So I guess you can do very interesting explorations until Friday with the tools that we showed you yesterday, and at the same time you can advance the structural tectonics of these explorations almost infinitively, right? So we're going to show some tools, but you're also invited to create your own strategies of employing the tectonic system in a very controlled but still differentiated manner. Right? So I think that's just a quick heads up. And tomorrow we split into groups. And should we have an exercise until tomorrow?
Do you want to simulate your own robot? Or?
Yeah, I think that would be fun.
Maybe I think you can play with files we provide in the Google Drive folder, and see if you can simulate the process of the simulate the fabrication process by yourself. I think we can make the process open. You can try to simulate what we are going to do, and maybe you can also try to simulate other fabrication process like mailing or like bricklaying or 3D printing. Maybe you can have a try if you can do it with plugin. Is that okay? What do you think, Jakob?
For me, it's okay. Yeah, sure. I guess we will go into deep with the robotic simulation a bit further down the road, right, on Thursday. But if you guys already want to play around with the tools that we provided today, then I guess we're super excited to have a look at your exercises tomorrow, similar as we did today. This gives us obviously also a bit of a feedback in maybe the areas where we should focus a bit further with the tutorials and stuff. So yeah. I guess, Jaihua, you said there's a couple of other questions regarding the simulation, right?
Yes.
So I guess we can go through those and then call it a day for the live stream.
The one from Canada. How can we export the Visual Studio code from Jet or 8? What Studio? Do you mean the G code for the robot? I don't think we have. If you mean the G code for the robot, then the Grasshopper, the plugin will generate it directly and automatically. Next, what we should do for tomorrow as practice, and I think we just talked about that. Would you please send this code for us? Yes, you will have that in the Google Drive folder. And can we export G code from Twitch to Kuka APP instead of working in real time? Yes, it's if you turn the auto file on the main server of your robot, it will just generate the G code directly, and you can use a USB to copy the G code to your robot manually. I think that's all the question.
Okay.
Okay.
Guys, have a good night. Have a good afternoon. And have a good lunch, I guess. And see you all tomorrow. Right?
And we will went back to the previous meeting room tomorrow.
Okay, I guess we'll just send another mail with the
okay.
The red link. Okay. See you guys. Ciao.
See you, Charles. And yeah.
Yep.
Yeah. Maybe we can have a meeting on